And what we're going to look at next here is we studied a little bit about exponential regression in our previous section, but we're going to look at it a little bit more today. We're going to do that along with logistic regression. Okay. So in this particular case, they give us a data table, okay, some real data that was collected for population of the United States for some different years here. So in this particular case, it says use the population data to predict the population for the year 2000. And compare with the actual 2000 population, which is 281 million. Okay, so we're going to make an exponential model for this by using our calculator. So let's review that process. We go Stat, Edit, and we want year 0 to be 1890. Okay. Again, we don't want to type in 1890. We want to type in year 0 for whatever the starting year is. Okay, and then after that, we're going to have our x's be years from the starting year. So therefore 1900 would be 10 years from 1890, and then 20, and then 30, and then 40, and then 50, 40 that is, 50, and 60, and 70, 80, and 90. 90 years from 1890 would be 1980. And then if we put the population data in, 62.9, keeping in mind that this is in millions here. So if we have to answer a question later, make sure we understand the units. Okay, I'm just going to type all the data in. And just for argument's sake, I want to look at the scatter plot of this data to see if it actually looks like it's exponential. So I'm going to go ahead and turn on my stat plot. It's already on. Okay. I'm going to change my window then to, I'm going to go -10 to 100 is fine, because remember my x's were from 0 to 90. So smaller than the smallest, bigger than the biggest. And in this case, I go from 62.9 to 226.5. So I'm going to go, let's say, 50 to 250. I'll put my scale at 10s here. And if we draw a picture of the scatter plot, I'm going to turn these off first so I don't see those in my y equals. And then I'm going to hit graph. And we see my scatter plot. Now, kind of difficult to tell really with this scatter plot. That looks almost like it's kind of linear, doesn't it? Okay. Now, they asked us to use an exponential model here, as you can see above here. So we're going to go ahead and find the exponential regression for that. So we'll go Stat, Calculate, Exponential Regression, and we get the following. Okay. So I'm going to write that equation down. So we get 66.9928047. That's our A. And our B is going to be 1.013976002. Okay. And I also want to note here that my R, okay, which is my correlation coefficient, okay, is 0.996. And remember, the closer that value is to 1, okay, the better the model is. So that's pretty close to 1, so this is actually a pretty decent model. And if we type it in, 66.9928047, and 1.012976002 to the x, and graph that alongside over the top of my scatter plot. Okay, I can see that in general it does a pretty good job of modeling that data. All right, and ultimately one of the things that might come up in a problem like this, if you were doing a real problem, is they might ask you, is this a better model? Is the exponential a better model than a linear model? Okay, remember, the key is this R value here. So if we were to do linear regression with this, okay, and see its R value, okay, if it had a higher R value or closer to 1, then we would go with the linear model, would be better, wouldn't it? Okay, if this R value is better, okay, then that means that it's a better model to use the exponential. So if we had to compare, we could do that as well. Right? Now, they also asked us to make a prediction with this model for the population in the year 2000. So if I were you, I would make my table on ask. And in my table, I need the year 2000. So that would be 110. 110 years after 1890. So if I plug in 110, I get 308,000. 370, if you will, rounded version. And they asked us to compare that with the actual. So how did we do? Not really very close, is it, in this case? Okay. Might a linear model have given us something closer, possibly? Could be. Okay. All right. And ultimately, that's kind of our job as a data analyst, okay, is to decide what model would be better. Okay, what model is going to be a better predictor of what's going to happen, okay, in the future. Now, keep in mind that we've seen this before. When we predict things in the future, okay, does the model always stay the same way? Okay. Matter of fact, we talked about population yesterday. Okay, even though this is growing exponentially, okay, what might happen with the population? It might actually kind of tail off and make it more of a logistic function instead of a exponential function. True? So let's go ahead and do the logistic regression and see what kind of equation we get for that. Okay, you also have in your calculator, under your stat, edit or calculate, if you go down to the bottom, you have a logistic regression. Okay. And so if we do logistic regression with the same data, let's go ahead and write down what equation we get, and we'll see how that does in terms of a predictor. All right. So notice that the general form is the form that has the e function in it. Okay. But they give you the values for a, b, and c. So if I were to write that down here, I would write c on top, 806.395173. And then 1 plus our a value here is 11.187222407 e to the, and then it would be negative 0.01642946494961. I'll be able to type that in here in just a second. Okay. So go ahead and put that in my y equals also. We'll see how that does for a predictor. So 806.395.173, and 1 plus 11.18722407 e to the negative 0.0164294961 x. And if we go ahead and graph the logistic function that models our data. Okay, it's graphing it right now. Notice it's very close to the exponential function. Kind of starts to taper off though here at the end and flatten out up to 806. Okay, we know it's going to be the c value here. And if we use that one to make a prediction, let's go ahead and go back to our table. That one's in y2. And notice this one, how much closer is that one to my 281? That's a lot closer, isn't it? Okay. So in terms of this population, okay, the logistic model would ultimately probably be a better model to use then, wouldn't it? Okay. Notice that your calculator does not give an R value either for a logistic model. Okay. Pretty sure that it doesn't ever. I don't know how to make it do it if it does, but okay. Okay. Questions on that one? Alrighty. I do want to talk about one vocabulary word that you have also regarding logistic functions. Okay. If we go back to the one that we just had right here for our population, okay, that c value that we have on top, I mentioned it yesterday, is essentially it's going to be the horizontal asymptote going to the right for a logistic model. Okay, that ultimately is kind of like our maximum number in terms of population. Okay, we call that in general the maximum sustainable population. Okay, I called it yesterday the carrying capacity. Okay, so whatever particular environment we're working in here, okay, that 806, which represents 806,395,175.3, if you will. Okay, that would be ultimately the maximum amount of people that this particular environment could handle. Okay, according to the logistic model. So that maximum sustainable population is going to be this. And remember on the graph, that's going to look like a horizontal asymptote. Okay, that's the highest the population is going to get. It's going to get infinitely close to that number, okay, but it won't actually get to that number. So that's going to be what we call our maximum sustainable population. Okay. So one more logistic model problem I want to look at, and then we'll give some of these a try. In this case, we have 1,500 students. This is a 5 students start a rumor, spreads logistically by the model given. Okay, and so in part A it says how many students have heard the rumor by the end of day 0. So if we were to plug a 0 in for time, okay, so again, t sub 0 is the day the rumor begins to spread. Okay, so by the end of day 0, okay, we could plug in our appropriate number. I'll go through in this case. If we plug in 0, we're going to get e to the 0, which is 1. And if we get 1 times 29, it ends up being 1,500 times 30, which gives us 50. So 50 students will have heard the rumor at the end of day 1, or end of day 0, I should say. Sorry. And then the other question says, how long does it take for 1,000 students to hear the rumor? So keep in mind that we would need to solve this equation. So once again, we're not going to solve this with algebra right now. Okay, so the only way to solve that would be to use our calculator, find the intersection between these two. So just like we did our other problems today, we'll graph both of those, and we'll go ahead and find the answer. It turns out to be about 4.5. Okay, so after about 4.5 days, 1,000 people would know the rumor. Okay, all right. And one last question that they didn't ask, but I will. This is 1,500 here, okay, on the top. This is our maximum sustainable, if you will. And think about why it's 1,500, because ultimately how many students are in the school? There's 1,500 students in the school, so could it get any higher than this? No. Okay, so it makes sense here for that to be our C value because of the amount of students in the school. Okay. All right, questions on anything regarding logistic models or exponential models?